Alright, so now we're looking at chapter 13, which is all about probability. And this is a really interesting section, but it's also a difficult section. There's a lot of unique ways of looking at things and a lot of ways that are kind of thinking outside the box and things that may seem pretty straightforward and easy, which turn out to be a little bit more complex. So make sure you guys are paying attention to these lectures and taking good notes and emailing me if you have questions because it will be challenging, but again, this is one of my favorite sections because it's just so interesting. Probability. Now, to start with probability, we're actually going to go back and review and relearn how to count things, which may seem strange, but all with probability, you have to know how to properly count things before you can actually calculate the probability. So we're going to start with how to count different things. One last thing before we get into the lecture is that the homework will not be due until Wednesday at midnight because today's lecture and tomorrow's lecture is kind of a single lecture combined, and you're going to be using today's lecture and tomorrow's lecture to do the homework. So if you can't do all the homework questions tonight from the homework, that's okay because tomorrow's lecture will give you more information on how to do all the questions. So don't get too frustrated if you can't figure it out immediately because tomorrow's lecture will be used. Alright, so enough of that being said, let's get into it. The best way to do these problems is just to go over practice problems and examples and kind of dissect how to solve each one. So our first question is, how many ways can you wrap a birthday present if you have 3 unique rolls? We have stripes, polka dots, and rainbow. And 3 different colors of ribbons, blue, yellow, and green. So we have 3 types of paper and 3 types of ribbon. Now the question is, if you have a birthday present, how many ways, notice the how many, we're going to be counting the number of ways to wrap it if I could use 3 different types of paper and 3 different types of ribbon. So what's the total number of options of how to wrap it? Well, we're going to start by doing a tree diagram. So a tree diagram just draws a picture of the number of ways. So let's first start with the paper. So let's say that our first branch of the tree is stripes, S for stripes. Our second branch is P for polka dot, and then we have R for rainbow. So 3 different options for wrapping paper, and then once I put the wrapping paper on it, I can use 3 different types of ribbon, blue, yellow, and green. But I could also have this option, blue, yellow, green. And sorry, it's a little bit messy, and I have these 3 options here, blue, yellow, and green. So that's all my total number of outcomes, different methods to get to the ways I could wrap it, but how many total ways can I wrap this? Well, I count each branch. I could go where there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's a total of 9 ways. Or I could have just counted all of these. 1, 2, 3, 4, 5, 6, 7, 8. 9 total ways to do that. So that's by using a tree diagram. And another way that we could do it, and this would be using what's called the fundamental counting principle. Which states that if there are n items and M1 ways to choose the first item, M2 ways to choose the second item. After the first item has been chosen, and so on, then there are M1 times M2 all the way up to Mn ways to choose N items. So that might seem a little bit confusing, but this principle is really important, the fundamental counting principle. And put simply, all you would have to do for this first example here is say, how many items do I have? If I'm trying to find the total number of ways, you're just going to multiply everything together. So I have 3. I have 3 here. This says to multiply everything together. So I just multiply and I get 9 ways. So when I use the tree diagram, that was a visual way of doing it. So you can kind of see all the different routes you could take to find the solution, but multiplying together using the fundamental counting principle, FCP, you just multiply everything together and you get the same solution. Question 2, how many routes are there from Antioch to Bay Point to Concord? If there are 4 roads from Antioch to Bay Point and 3 roads from Bay Point to Concord without backtracking. So let me add a page really quick, put this on. Okay. So let's draw a picture. We'll do it both ways. You might have already figured it out using the fundamental counting principle. But let's just start with a picture. So I'm going from Antioch to Bay Point to Concord. It says there are 4 roads from Antioch to Bay Point. There are 3 roads from Bay Point to Concord. Now, I can count each of the roads, and I can go, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there are 12 ways to count, or 12 different routes, I should say. So given this situation, we can count that there are 12 different routes in this given scenario. Now what if I add, in addition, there are 6 roads from Concord to Danville. Let's say I add another 6 roads from Concord, 1, 2, 3, 4, 5, 6, from Concord to Danville. Now that's going to get really complicated really quick, because if I'm going to count my first one, this would be 1, and I have to go 2, 3. It's going to get really confusing because then I have to come through the bottom. It's going to be very complicated to do it that way. So the picture, the tree diagrams, those work in simple situations, but hopefully you see how complicated it can get by drawing a picture. So what's a better way to do this? Let's use the fundamental counting principle. So going back to our first example, or this example here, where the answer was 12 ways, notice that I had 4 roads, I had 3 roads. The easy way to do this, 4 times 3 gives me 12. So the fundamental counting principle is a lot easier, but it's important to know what the picture looks like so you have an idea of what's going on. So looking at this one, if we have an additional 6 roads, so I started with 4, 3, and I also have 6, so the fundamental counting principle says just multiply everything together. And that is going to give me 72 routes. So you get a total of 72 different ways by going from Concord to Danville, or from Antioch to Bay Point to Concord to Danville. And just try to picture if you had to count, like that first diagram that we had, where it was like this, and all these different routes. Like imagine counting 72 different routes with that picture. It's going to be really complicated. That's why the fundamental accounting principle is the best method to use. Alright, so we already did that. Ignore that. Let's look at example number 3. And you'll see in your notes all these boxes here. Leave those blank for now because there's actually another way to solve these problems with these boxes using permutations and combinations, which we're going to go over tomorrow, and we'll come back to these questions and answer them using a different method. So there's different ways to do these. You can use just counting, basic counting, or you can use permutations and combinations. But we're going to start with just doing a straightforward counting way. Question 3 says, how many ways could you cast the parts for the play Cinderella if you have to cast Cinderella, her evil stepmom, and her 2 stepsisters, and you have a pool of 10 actresses. So you have 10 actresses to choose from. So the way to picture this is you have 10 people, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you have 10 people, and you only have 4 different spots open. Okay. So that's kind of the picture you can think of to start with. So using these 10 actresses, let's say we have Cinderella, the stepmom, and stepsister 1 and stepsister 2. So how do we figure, using the fundamental accounting principle, how can I figure out how to do this? Well, let's look at the method behind the counting first. Let's say that I were to pick this person here. So they're taken and they go into the spot here. So for my first option, for this opening here, how many people were available? That's what you have to think. What's my total number that were available? Well, I had 10 people to pick from. I chose that person. They're in. So now, for the stepmom, how many people are available? Well, now, I have 9 people remaining. I pick a person. Now I only have 8 people remaining. So there's 8 options here. And once they're chosen, I only have 7 people remaining for the final stepsister. So you kind of see how the fundamental accounting principle works. We have 10 times 9 times 8 times 7, which gives me a total of 5,040 different ways, which is pretty crazy to think about. Given these 10 people here, the original 10 people, there are 5,040 different ways that I could pick each of these people to play the parts. And maybe it's a little bit confusing why there's so many. When you start thinking about it, if I were to start from the beginning, I could have chosen this person to start for Cinderella, then I could have chosen this person, or I could have started with this person as Cinderella and then gone to this person as the stepmom. There's just a bunch of different ways to pick all these people. So you get really high numbers really quick. So if you start getting big numbers for your solutions, it's okay. Alright, here's example 4a. Let's say that we had Perry the Platypus needs to crack Dr. Doofenshmirtz's key code to his top secret laboratory so he can prevent mayhem. I think it's Phineas and Ferb, I don't know. The code begins with a capital letter and is followed by 3 digits. So the picture here is that we have a code, so 4 digits, or 4-part passcode, and our first the code begins with a capital letter, so A through Z, and is followed by 3 digits. So I have 0 through 9, 0 through 9, and 0 through 9. So when we look at this, how many letters, capital letters, are in the alphabet? Well, I have 26. How many digits? 0 through 9? Well, there's 10 options there. We have 10 options here, and 10 options here. So using the fundamental counting principle, I multiply all these together, and given the situation, the number of possible codes for this given block is 26,000 different possible codes there. And that's just using a 4-digit or 4-part code. So picture your iPhone. How many different, if you have a 4-digit code there, how many possible ways you could enter a code. Now I know that a lot of people have, thumbprints and Face ID and whatnot, but I'm still in that iPhone 5 game, so I still have to enter my code. So let's say that you have a 4, and this is not in your notes, but say you have a 4-digit passcode, and if we were in class, what I've done the last couple of years is I give somebody my iPhone, and I say, try and guess the code. Like, if you guess the code, I'll give you extra credit or something. And so I give them my code, and the reason I'm so confident that they won't guess the code is because how many different ways can you enter the code? Well, you have 10 digits. I have a 4-digit passcode, so 10 times 10 times 10 times 10. And that comes out to 10,000 different ways, which quickly, if you were to calculate the probability, that would be 1 over 10,000, which if you convert to chance, that would be, what is it? It's 0.01%, if I did that. 1 divided by... Yeah, 0.01% chance. So it's very unlikely that somebody would ever guess my code, which makes it kind of fun. Fun little activity in class. Anyways, let's look at question 4b. What if Dr. Doofenshmirtz only used numbers that were divisible by 5? So before we do that, we have to think about what numbers are divisible by 5. So we look at the numbers 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So which of these numbers are divisible by 5? Well, we have 0, because 0 divided by 5 is 0. And then that doesn't work, no. 5 divided by 5 equals 1, so that one works. And the rest do not work. So the number of numbers that are divisible by 5 is 2. We only have 2 numbers. So how does that change everything? Well, for his first code, he still has a capital letter, so we still have 26 options here. The second number now, it's either going to be 0 or 5. So there's 2, and 2, and 2. So multiplying these together, we get a total of 208 ways. So there are 208 ways you could possible codes there for this given situation. Number 5, how many ways could you order a lunch special off this given menu? So using the fundamental counting principle, let's look at, we have our entrees, we have our side dishes, and then we have our drinks. So what are the total number of ways that you could order off of this menu? Well, for our entrees, we have 3 options, For side dishes, we have 3 options. For our drinks, we have 4 options. So using the fundamental accounting principle, that is going to give you 36 ways. Number 6, if you have an alphabet, hopefully you guys remember or know that there are 26 letters in the alphabet. How many 3-letter words can you make with when any sequence of letters counts as a word? So we're just looking at a 3-letter combination of letters, and we'll count that as a word. So it doesn't matter what they say, we're just looking for 3 letters together. Now the question we have to ask yourself is, does it matter if we repeat? So for example, let's say I use A. That's going to be a word, we're going to count that, and the repeating of letters is okay because the question doesn't state otherwise. So we have 26, so for my first letter, I have 26 options. My second letter, I also have 26 because I can't repeat. And third, I have 26, so I get 26 cubed, and that's going to give me 17,576 different words, quote unquote. And that's again using the fundamental counting principle. Now what if the 3 letters all have to be different? So I can't do this because I'm repeating letters, so no repetition. Everything has to be different. So I could use A, B, C, I could use B, C, A, I could use C, A, B. Those are all fine because there's no repeating in each of the combinations or each of the groupings. So how do we figure this? Well, for my first option, I could use A through Z. So I have 26 options for my first letter. Using the fundamental accounting principle, I'm going to multiply. The second option, well, I can't repeat. So let's say I used A. A is out, so how many letters do I have left? I have 25. We'll say I use A and B. A and B are out, so now I only have 24 options left. So every time I use a letter, I get rid of it. I take it out of the pool, and there's one less. So when I multiply this, that gives me 15,600 words, quote unquote. So you really have to be reading the question thoroughly and asking yourself, what exactly is it asking? Number 6, 6C, how many 5-letter excuse me, how many 5-letter words can you make if you can repeat letters but cannot have 2 in a row that are the same? So what does that mean? Let's figure out what that question is actually stating. So I'm looking for a 5-letter word. 1, 2, 3, 4, 5. But I cannot have 2 letters in a row that are the same. So if I went A, B, C, D, this would not work because these 2 letters are repeating. So that wouldn't count. What about this? Could I go A, B, A, X, Y? Even though I'm repeating these 2 letters, it's okay because they're not next to each other, they're not in a row. So hopefully you guys see A, B, A, B, A. That's okay because there's no repeating in a row. They're not next to each other. So when we look at this, I have 26 letters for my first option. Well, let's say I used A. I can't use A again, so how many letters are left over? 25. Let's say I used B for my second letter. Well, how many letters can I use for my next one? Well, now the only option I can't use is B. So there's 25. Let's say I use A again. The only letter I can't use is A, so I still have 25 options. And same thing for my last one. So I have 26 times 25 times 25 times 25 times 25. 26 times 25 times 25 times 25 times 25, which gives me a total of 10,156,250 different words or letter combinations. So a lot of different ways. This one's interesting, number 8. Kind of an interesting question there. Hold up, I missed one. Rewind. I forgot to erase this. Okay. This one's interesting too. A little bit of a unique question. Number 7. How many ways can you choose one thing from a set of 2? So let's just say I have 2 items. Let's just say A and B. Well, if I only wanted to pick one thing, how many ways could I do it? Well, I have one way to pick A, I have one way to pick B, so there's only 2 ways I could do that. Let's say I had 3 options. Well, if I'm only looking to pick one thing, how many ways could I do that? Well, if I'm only looking to pick one thing, that's one thing. That's my first option. 2, 3. There's only 3 ways here because I'm only picking one thing. Let's say that I had 4 items. If I only want to pick one thing, that's 1, 2, 3, 4. There's 4 different ways I could pick one thing. So when you have n items, the number of ways you can pick one thing from n items is just n, the number of items you have. Number 8, how many ways can you choose 3 things from a set of 4? Well, if I have 4 items, A, B, C, we'll say X. If I'm picking 3 things from a set of 4, well, let's kind of figure it out. A, B, C, that's 1. I could go I could go B, C, X, that's 2. I could go, B, C, X, X, C, A, that's 3. C, A, B, X, B, C, X, X, C, A. And the last one that I'm missing is C, A, B, X. Just one moment. XB, that's it. XBA. So that's my last option there. So there's 4 different ways I could do this. So our little formula here is that you can pick n-1 things from a set of, or if you're trying to pick n-1 things from a set of n, there are n different ways. So I have 4 items here. I was trying to pick n-1. I was trying to pick 3 items from 4. So therefore, if you have that situation, there's going to be n different ways to do it. So 4 different ways to do it in this case. So let's say really quickly, if you had 5 items, you're picking 4, that's n-1, there would be 5 different ways to do that. Okay, almost done. How many different orderings of the letters A, B, C, D are there? So now I'm just looking for different orderings, so different rearrangements. So to do this, I have 4 letters. Oops. I have A, B, C, and D. So I want to rearrange these however I want. I could go DC, AB, I could go BC. It's like, let's just look at the first one. A, B, C, D, that's one way. I could go A, C, D, B, that's 2 ways. I could go A, D, B, A, that's 3 ways, and it just keeps going. So how many different options do I have? How many different ways? Well, let's just use the fundamental accounting principle. And for my first option, I have 4 different letters. Second, 3. Third, 2. And last one, I have only 1 different letter remaining. So I get a total of 24 different ways to do this. I could write them all out and get 24 different ways of doing it, but using the fundamental accounting principle is much easier. Alright guys, I think that's where we're going to stop for today. The video is getting kind of long. I don't want to overwhelm you with information. So tomorrow we'll finish up this first section of notes. And then remember, the homework is not going to be due until Wednesday night. So you have a few days to go over it. So if you don't completely get it tonight when you're working on it, that's okay, because tomorrow's lecture should give you more information on it. All right, see ya.